Hey, good afternoon, everyone. Thank you for joining us today on this sunny, lovely, hope you're enjoying the tail end of summertime. Welcome to tonight's digital design series. If you can see my screen, and I think you can, we have our series of community agreements through the COTE. My name is Matt Bokar. I'm a PM with Carlton Hart, and I also do a little bit of volunteering with the AIAO COTE, among Heather and Colleen and Kathy. My colleague Ellen, who is here in the room, will be keeping an eye on the chat for real-time questions during the presentation, and then Ellen will be handling the Q&A at the very tail end. We just want to pause here so everybody has time to go through our community agreements. We remind everybody the space is respectful, it's comfortable, it's open, it's curious, it's inclusive, and it's kind. So we just wanted to welcome everybody to this is our September 2023 DDS Digital Design Series. Today's presentation will be given by Jim Schneider. I'll kick it over to Jim in a second. The topic is developments in sustainable precast. So here's our Zoom reminders. Mute your mic during the presentation, unmute during the discussion. Reminder about your camera and speaker view. If you haven't already signed up for continuing ed credits, Kathy, Colleen, Heather can help you out. And just a reminder, this presentation is being recorded. So with that, I'm going to stop sharing my screen, kick it over to Jim Schneider to do a self-introduction, and then take the presentation away from there. Thanks, Jim.
All right. Thank you. Appreciate it, Matt. Good to be here with everybody. Let me get my presentation up quick. All right. So thanks for coming. Today we're going to be talking about, the title of this presentation is Innovations and Operations Developments in Sustainable Precast. And so I am basically the executive director of PCI Mountain States. So I'm based in Denver with our basically our chapter of PCI, which is the Precast Prestressed Concrete Institute. The Mountain States chapter covers Colorado, Wyoming, Utah, Montana, and Idaho. And we often do a lot of work with Knife River and some of the other producers in Oregon and Washington, and have had involvement with AIA Oregon for a few years, which has been great. So I appreciate you guys taking the time to be with us today. A little bit about me, as I mentioned, executive director of PCI Mountain States. I have been working in the design and construction industry for about 2 decades. I was previously in publishing and doing a lot of architectural publications. I've written for things like Architect Magazine, EcoStructure, and a few others. I still contribute to several industry publications. And, also, as I mentioned, lived in Denver, father of 2, passionate about sustainable design. And I happen to think concrete's pretty cool, even if my kids don't. Got to share a little quick anecdote. I recently got to be interviewed on a podcast called This is Concrete. Pretty interesting. So I got the link as I was driving with my kids and decided to listen to it. And they're like, "Dad, is that you on the radio?" And I said, "Yes, yes, it is." And so I listened to it for a little bit. And then after about 5 or 10 minutes, I looked in the back seat, and here's what my kids were up to. So they apparently don't find concrete quite as interesting as I do. But I think we got some pretty cool things to talk about in this presentation. It is registered for one HSW learning unit for AIA. And so we'll get you registered for credits there. Little note about the course description. Precast is a durable, resilient material that can provide many benefits to efficient, sustainable designs in the long term. While concrete does have an upfront CO2 impact, the industry is working to reduce greenhouse gas emissions and increase the efficiency of its products. This presentation will discuss some technical innovations to reduce the carbon footprint of concrete and examine current process improvements that are pushing the industry forward to a more sustainable future. And I'm actually going to just go ahead and stop my video and just keep the screen up here. But we'll kind of keep this casual and move along here. So learning objectives, we're going to learn about attributes, benefits, and considerations of using precast in the holistic design of sustainable structures, examine established and developing technologies aimed at reducing the environmental impact of precast concrete, discover process improvements, production efficiencies, and other producer efforts that are creating greenhouse gas reductions today, demonstrate ways that concrete producers are lowering the environmental impact of their products and how projects are achieving sustainability goals with concrete. So I really think, the reason I recently, this is a fairly new presentation, and the reason we developed it was that it's really thinking about this idea of building for tomorrow. In the concrete industry, we certainly talk a lot about the life cycle benefits of concrete, its resilience, its durability, the fact that its impact is spread out over a very long life. But the fact is we all know that climate change is here. We're seeing it every day. The IPCC climate or reports that have come out of the UN in the last few years have really shown that we're not only in the midst of it, but it's expected to only increase in the coming decades. So we have to be thinking about how can we build structures that are going to be resilient enough to deal with the challenges that are coming in the future, but also how do we deal with the immediate issue of reducing carbon and greenhouse gas emissions? And it's really important to go with both of those things in mind. So, which is why I think it's important for us to talk about some of the things that the concrete industry and the precast industry specifically is doing to look at reducing that CO2 impact. Some of it is, pretty early stage of development. Others of it are a little bit more established, but, there's a lot of interesting things happening in the industry. We certainly take the idea seriously. Just kind of a few notes to start with. I mean, the idea of sustainable design, I mean, certainly we see a lot of different definitions. I like this one from the U.S. General Services Administration. Sustainable design seeks to reduce negative impacts in the environment and the health and comfort of building occupants, thereby improving building performance. Basic objectives of sustainability are to reduce consumption of non-renewable resources, minimize waste, and create healthy, productive environments. It's basically the idea of achieving as much in terms of performance as you can while doing as little harm to the environment as possible. And why do we care about this in the construction industry? It's, of course, because we have a very big footprint, both in terms of materials, energy, carbon, all of that. So according to the United Nations Environment Program, buildings and their construction worldwide account for about 36% of global energy use and 39% of energy-related carbon dioxide emissions each year. U.S. Energy Administration data from 2018 shows that residential and commercial buildings account for about 40% of energy usage in the United States. According to USGBC, buildings account for about 13.6% of potable water use in the U.S. The building industry consumes about 40% of the raw materials flow of the entire global economy each year. EPA further estimates that 569 million tons of construction and demolition waste were generated in the U.S. in 2017, more than twice the amount of generated municipal solid waste for that year. So these are the reasons why any improvements we can make as an industry. Some more statistics from Architecture 2030, buildings account for about 28% of global emissions each year, about 11% of embodied carbon emissions. So because we have such a footprint, we have such a impact on overall greenhouse gas emissions, energy, materials, everything like that. Any improvements we can make as an industry really can make a difference worldwide. So this is why we are obviously so focused on it as a profession, have been for many years. This is why we take it as seriously as we do. So we are working in the concrete industry towards carbon reduction in a number of different ways. The concrete industry recognizes the need for immediate reductions in greenhouse gas emissions. Again, we talk a lot about life cycle, which is important. It's a factor that we need to discuss as well, but we also recognize that we have to find ways to bring down the greenhouse gas impact of concrete as a material. So we have numerous new technologies and techniques are emerging to minimize the initial impact of manufacturing concrete. Kind of talking, a little bit about embodied carbon, because of course there's lots of different definitions of that. Some view the embodied carbon of the building as including the entire life cycle of the materials, including the operational phase, and others tend to look at basically like the cradle to gate piece of embodied carbon, so just the extracting, manufacturing, and transport. That's kind of where most, when we talk about embodied carbon right now, that's generally where the metric is cradle to gate, because we simply don't have a lot of the data yet for the cradle to grave. But I think it's kind of important when you're looking at embodied carbon to recognize what that means, because certain materials are going to look better cradle to gate, others will look better cradle to grave. And we want to certainly make sure that you're comparing apples to apples when we're talking about that. And in terms of materials, I mean, all building materials contribute to the carbon footprint of a building in different ways. Of course, concrete contributes about 6 to 11% of global CO2 emissions. Most of it comes from the production of Portland cement, which comprises about 10% of the concrete mix. Producing aggregate also requires some energy, and a lot of that comes from transportation, which is why certainly in the precast industry, we really encourage the use of relatively local aggregate instead of having a project in Oregon that might have where the designer might ask for some particular concrete mix with an aggregate that's out of Georgia or something. You want to avoid that and keep the transportation down. So steel also, of course, manufacturing virgin steel from iron ore is very energy intensive. The global steel sector has a large carbon footprint, contributing upwards of 10% global CO2 emissions as well. Wood, its manufacture produces fewer emissions than steel and concrete, but there's also kind of a deeper discussion of the overall impact. We kind of need more research on that cradle to grave piece of it to understand the full carbon emissions of the length of the material's life, the carbon emissions from logging, processing, transport, maintenance of wood products also. So there's some things there too. Everything's got an impact. And one example, just kind of looking at it in a little bit of a different way, is this is a study from the International Institute for Sustainable Development, looking at kind of the different manufacturing construction impacts of concrete and wood. So what you see is obviously the manufacturing side of things. Clearly, concrete has a much bigger impact and has a little bit more of an impact construction. But there's also biogenic carbon loss that comes from actually carbon that gets emitted from taking the out of the soil when you take the trees out, and you're also replacing old growth trees with new growth trees, so less carbon is absorbed. So there are some impacts being studied on that front, which can sort of change the equation a little bit. And then if you look at the use phase, and again, this is more like the cradle to grave idea of like actually factoring in the operation of the building, which is really where most of its impact in terms of energy and carbon comes from, is over the operation of the building over time. You can see that the use phase really does level out between the materials. Now, of course, as we were discussing before, we do have the need to reduce carbon in the short term, which is why, in addition to the life cycle benefits of concrete, we're thinking about ways to reduce that impact up front. So in essence, all building materials have carbon costs. The challenge for designers is to consider all the benefits, attributes, and costs, and specify a material mix that best suits a project's environmental goals. I mean, obviously, every project's different. There's no such thing, I think, as like a green product. It's mainly how do you use a mix of materials and systems to come up with the best design that's going to provide a good space for occupants and also create as little impact to the environment as possible. So precast concrete has an upfront carbon impact. It mitigates that impact by delivering a high level of performance over a long life cycle. Buildings can last for a very long time, be very flexible. So there's some real long-term advantages in that. And of course, when we're talking about concrete, there is often the discussion that, well, it is a big, carbon impact right now, and cement is an issue. However, that being said, it is the most abundant man-made material in the world. Estimates range between 4 and 10 billion tons of concrete are poured globally each year. Concrete does provide a lot of positive attributes, including durability, resilience, quality, energy efficiency, a lot of things. We need it in essence. So what we need to do is make it better. It's not as simple as just saying, oh, let's just stop using concrete. Well, we do need to use concrete. So it's important for us to figure out ways to do it in a way that's less impactful. And it is a high performance material that integrates easily with other systems, inherently provides a versatility, efficiency, and resiliency needed to meet the multi-hazard requirements and long-term demands of high performance structures. And just a quick definition of high performance structure from the Energy Independence and Security Act of 2007, one that integrates and optimizes on a life cycle basis all major high performance attributes, including energy and water conservation, environment, safety, security, durability, accessibility, cost benefit, productivity, sustainability, functionality, and operational consideration. So the reason I bring up the high performance idea is that because the goal is to have a building that can last for a long period of time and provide all those benefits over an extended lifespan. And, just not going to go over everything in the slide, but the essential attributes and benefits of precast that we talk about generally as a system And by the way, I should, really clarify, we're talking about precast pre-stressed concrete. This is produced in an offsite in a plant, PCI certified plant, like, somebody like Knife River or Missoula Concrete or Contact Engineered Solutions or some of the other precasters that might be in your state or you've done work with, that are PCI certified. So it's produced offsite, shipped to the job site for very quick assembly. So it's very versatile. You can use it, can take on a lot of different aesthetic looks, and also can be structural and architectural at the same time. Can be recycled and are used in adaptive reuse, and we'll touch a bit on that later in the presentation. Also has a lot of efficiency in both site efficiency, schedule efficiency, and also when you're talking about like insulated sandwich wall panels, energy efficiency. I just finished working on a case study of Pikes Peak Visitor Center, which is up at 14,000 and change feet, with walls that, by using the thermal mass impact of concrete, was able to achieve like R68 or something crazy like that, because the weather's so insane up there. So there's lots of possibilities there. And it's very resilient. It's strong, durable, lasts a long time, stands up to storms, earthquakes, blasts. These are important things, like we were talking about earlier, the impacts of climate change to come. We want to think about buildings that are not only creating the least impact now, but we make sure that they last and stand the test of time, because there's nothing less sustainable than having to tear down a building and build a new one. We saw the materials statistics. So concrete in general, and precast specifically, is versatile. Can be exposed to the elements, exposed for architectural reasons. It's economical depending on its use, available everywhere, made from abundant materials, usually local materials, doesn't rust, rot, or burn. So again, its impact is primarily an upfront impact, but once it is in, it's pretty inert and stands the test of time. So it's used on bridges, lots of different types of buildings. We see precast used on, of course, parking structures a lot, but we also see it used on offices. There's a lot of precast offices here in Denver. Lots of schools and things of that nature. So it's a handy, versatile material that can be used in a lot of different ways. Again, some of the statistics about how much concrete is used. 3.4 trillion square feet of concrete will be poured by 2060. That's I take that back. I'm sorry, this isn't concrete. This is buildings. This is construction of buildings. So we're expecting to have 3.4 trillion square feet of new buildings by 2060. That's 1.4 times existing building stock. So obviously construction isn't stopping. We have to really think about how we can design zero energy buildings, how we can use the materials as smartly as possible, and reduce those embodied impacts. So concrete is useful for a few different reasons. Thermal mass, as I mentioned a little bit earlier, but thermal mass is basically the physical quality of concrete, where it acts like a thermal battery. It slows the movement of heat energy through a wall, so it kind of slowly absorbs and slowly releases heat, creates a more even temperature, can give you a lot more of a energy efficient HVAC system, because the temperature doesn't swing as much. It goes to off-peak hours. There's some advantages there that you can actually calculate through ASHRAE and up the R value of your wall system by utilizing thermal mass, which is there anyway. It's physics. So that brings energy efficiency. We have some case studies of projects that were able to downsize their HVAC by like 30% by using, taking advantage of thermal mass. Also, disaster resilience, it's very strong, durable. So the challenge is, how do we offer all those benefits and then decrease our carbon footprint too? So that's what we're really diving into as an industry now. So two big sources of carbon during cement manufacturing. So this is some information from PCA, the Portland Cement Association. Cement is, of course, the first and critical ingredient in concrete. U.S. cement industry, based on EPA carbon emission data, manufacturing of cement accounts for about 1.25% of U.S. CO2 emissions. Process emissions, take the calcium carbonate and drive off the CO2. That's about 60% of the emissions. Material temperatures, creating the actual cement and clinker, it requires a lot of energy for the temperature, so that's part of the impact as well. So PCA recently released this document, which is kind of an interesting, skim of the roadmap to carbon neutrality. So it's the idea of how do we as a concrete industry get to a carbon neutral place, in different ways. So it's really reducing that use of cement and making it more efficient, so that we don't create quite the carbon impact. Um, this is just kind of links in the value chain when we're talking about concrete and some of the things that you see. Clinker, the key chemical reactive ingredient. Cement is the binder. So, that's important for that reason, but it's also, yes, it's a big impact. Concrete, critically useful to material in society. Construction is obviously a part of our, way of life. And then there is the idea of concrete as a carbon sink, which I'll touch on a little bit later too. But there are studies to show that as concrete ages, it actually reabsorbs a significant amount of the concrete it releases, which again is nifty in the long term. But we have to be thinking about the immediate impact as well. So optimizing cement, part of what we want to do as an industry, and this is talking about concrete broadly, is right size the amount of clinker and cement, use more non-gypsum additions, recognizing the benefits of Portland limestone cements, which can really impact the carbon footprint of some of these materials, choosing the right cement specification for specific applications, and then also be thinking about zero emission bulk transportation, whether that's rail, truck. That's part of the equation too. We have to take out the emissions that are coming from that. But it's really coming up with the most efficient methods and materials to make this with. And part of the advantage with precast is that because it is a plant produced material, you really do have that control over the process. That makes a big difference. So 3 main goals when we're thinking about this as an industry: we want to reduce the use of traditional Portland cement, offset or mitigate the carbon emitted in the production of concrete, which is another piece of the approach, and then also increase strength while reducing material use. So try to do more with less. So some improvements we're seeing in the world of cement is, and you may have heard of some of these, but Portland limestone cement, or PLC, limestone calcinated clay cement, or LC3. And these are cements that essentially decrease the carbon impact of cement. It's a less carbon impactful version. And also utilizing more energy efficient heating technology, which is also something we're seeing in like the steel industry. So we're trying to find ways to heat these things that don't utilize so much energy. So Portland limestone cement is a blended cement with a higher limestone content. So it works the same as traditional Portland cement, measures the same, and performs the same. There often can be minimal adjustments in mixed designs, can reduce the carbon impact by about 10%. But of course, it is, because it is something that is a little bit different and can have some variation, engineers can sometimes be a little bit wary of just going 1-to-1 and thinking it's going to be just right. So, there's still some kind of feeling it out with PLC. But it is becoming more prevalent. We're seeing it quite a bit more in specifications, and more producers are starting to use it. There's also limestone calcinated clay cement, or LC3. This is based on a blend of limestone and calcinated clay, made using limestone and low-grade clays, which are available in abundant qualities, and cost-effective, and doesn't require capital-intensive modifications to existing cement plants. This can reduce CO2 emissions by up to 40%. So again, this is, kind of getting used to some new, thinking about mixes in a slightly different way, but there can be some real impact in terms of carbon with LC3 as well. In terms of procuring PLC concrete, it's a simple revision to specifications. It's a 1-to-1 replacement of OPC and PLC, usually the same suppliers for your ready mix or precast. Same delivery, placing equipment. Long track record, history of good performance, even at higher limestone contents than the U.S. Europeans introduced this in the late 1960s, as usual. They're ahead of us. Canada's been using them since the 2000s. So, this is something that's fairly well established, and we're really kind of starting to catch up to it here and see more of it. So PLC allows for the same dosages also of fly ash and other pozzolans and slag cement for materials that we can use in replacement of cement to a percentage. I'll talk more about that in a bit. As with any new material, some testing is warranted to confirm effects on fresh and hardened properties. Air content, slump, bleed potential, setting time, compressive strength. These are all things that you want to work with your precaster on to make sure that you are hitting the right marks and all that. So mixed designs of PLC workability doesn't seem to be any particular increase or decrease. Bleeding decreases with increasing fineness, generally no concern. Setting time can be a slight decrease with increasing fineness. Heat of hydration, slight increase at early ages, but less significant at later ages. Compressive strength can increase slightly, both early age and long-term strength. Scaling and freeze thaw resistance using some same techniques with OPC concrete mixes, proper air void systems curing higher strengths, and similar sulfate resistance also. So there are calculators. You can go to greenercement.com for CO2 savings, kind of look at the benefits of using PLC, spec language, case studies, availability, things like that. Lots of resources. DOTs are starting to use these more. I'm certainly hearing about a lot of that in different parts of the country. Ways to reduce carbon in the infrastructure work that we do. ASTM and AASHTO specifications are harmonized. They have the same requirements. Delaware apparently as recently became the 45th state DOT to accept PLC. So pretty much everybody at this point. PLC availability, you can see just about everywhere. We got some up in the Pacific Northwest there. Obstacles to optimizing concrete, prescriptive based specifications, limits on how much supplementary cementitious materials can be used, restrictions on the use of fly ash as an SCM, minimum requirements for how much cementitious materials should be used, limits on water cementitious materials ratio. Essentially, like we, as an industry right now, we're really working to gather data so that we have a good baseline of where we can build from. And we're trying to avoid sort of the prescriptive type of requirements. But there are a lot of states and municipalities that are starting to require some better than industry average EPDs and things like that. And we'll talk a bit more about that later. So it's really, it would encourage a shift from prescriptive to performance-based specifications so we get a real understanding of how it works and what is happening with it. Incentivize innovation with today's products instead of institutionalizing inertia with yesterday's practices. The right mix using the right materials for the right application can really give you the right performance. That seems kind of the important message here. So, as I mentioned, one of the things we've been doing for a while is using supplementary cementitious materials. One of those goals I mentioned before was just reducing the amount of cement we're using in general, whether that's traditional Portland cement or one of the, PLC or LC3 kind of cement. If we can replace it with something that creates less carbon, that's another, win as well. So one that we've commonly used as an industry for a long time is fly ash. So as a coal byproduct, commercially available fly ash is a finely divided residue that results from the combustion of pulverized coal and is carried from the combustion chamber of the furnace by exhaust gases. So the thing with fly ash is you can use it in certain percentages. Again, in the precast industry, we've used it quite a bit for a while. It depends. It's something you need to talk to your precaster about, depending on the application, what you're looking for, curing time and all that. That sort of determines what percentage of it you can use. And the other thing with fly ash is that, frankly, as we, hopefully start to use less coal, that will become less available. So we have to certainly be thinking about other things as well. So slag cement is a glassy granular material formed in molten iron blast furnace slag is rapidly chilled. So this is hydraulic and can also be added to cement as a supplementary cementitious material. Similarly, silica fume is a finely divided residue resulting from the production of elemental silicon or ferrosilicon alloys carried from the furnace by exhaust gases. Silica fume, with or without fly ash or slag, is often used to make high strength concrete. So these are all basically waste products from other industrial processes that can be used in replacement to a percentage for cement in various concrete mixes. But there are some really interesting other concepts sort of coming to the fore that, many of these are very early stage or, may exist on some level, but hasn't been done at a large scale yet. But ways to replace cement essentially with something more less impactful, more natural, One of those things is biochar. So this is a waste-derived carbon-based material that sequesters carbon. This can be generated from wood materials, biosolids, even manure. So different organic materials can be used to make biochar. So this, from a report called Biochar Augmented Concrete, was published in Chemical Engineering magazine. Study proposed a revolutionary design of carbon negative concrete with a large volume of biochar incorporation, and elaborated the roles of biochar in cement, hydration, and microstructure development of biochar augmented concrete. The total CO2 emissions and economic values of biochar augmented concrete were, for the first time, quantified by conducting life cycle assessment and cost benefit analysis. Biochar as aggregate in concrete promoted the cement hydration process, facilitating the formation of calcium silicate hydrate gel and enhancing the polymerization degree via internal curing. So basically, this study was done that shows a significant carbon decrease by using biochar. There's also this article in a publication called Interesting Engineering that talked about a study that was done at Washington State University, where traditionally, I think you'd see biochar used at like about 5% in a mix. They were able to do some kind of process with the biochar where they washed it with like some of the concrete wastewater, or did some kind of process with it, and they got it up to like 30%. And that really sucked up about 23% of its weight in carbon dioxide from the air, while still achieving a strength comparable to ordinary cement. So there's some interesting study going on in that area that could be, a possibility, again, as a sort of replacement for some percentage of cement. Another thing is calcium carbonate aggregates. These are a synthetic limestone made from industry CO2 and calcified water. This will continue to reabsorb CO2 throughout its life, can bring about as much as a 40% reduction in CO2. This is kind of there's a group called Blue Planet that's doing this, and it's really cool. But right now, it's kind of in short supply, so we're working to scale that up. It's there's some good possibilities here, but it's not really at the quantity to do anything like at a big scale just yet. But Blue Planet Systems' idea is to capture carbon dioxide emissions from power plants and other sources and use the CO2 to manufacture aggregate, which goes into making concrete. If successful, the firm claims it will end in a double win. First, carbon dioxide from the production of energy is diverted from being emitted to the atmosphere and instead sequestered. And second, the synthetic aggregate results in reduced emissions that would have associated with the production of cement and concrete by conventional means. So this is another way to attempt to use waste products essentially in a productive way that brings down the carbon impact of concrete. Recycled glass. This is another interesting possibility. So for more than a decade, a group in New York called Urban Mining Industries has been advancing a new use for recycled glass in the form of a product called Positive. Ground glass pozzolan used in concrete production. Like other artificial pozzolanic materials such as coal fly ash, ground glass can assume cement-like qualities when it reacts with a combination of water and cement. So basically, it starts with a chemical reaction when it's paired with water and cement, and the hydration of cement introduces two key compounds. One is calcium silicate hydrate, which is basically the glue that develops the concrete strength, and the other product is calcium hydroxide, which conversely weakens the concrete and causes porosity. When a ground glass pozzolan is introduced, it gives up a silica atom and joins in the CH to become CSH. So the pozzolanic reaction allows ground glass to gain cementing properties and act as a partial replacement in most mixes, usually about 20 to 30% in most mixes. So there's some interesting possibilities there too. So that's a little bit more localized. I don't know if that's really gone much nationwide yet, but we have seen some work with that. I'm just seeing it. So microalgae, this is another interesting. Hold on a second. I'll go back a slide. Oops. Okay, here we go. So algae. This one really fascinates me. And again, this one's not not happening right now, but was scaled out maybe someday. This is an interesting prospect for the future. So the idea here is to actually make cement limestone. Right now, we make cement limestone from extracting it from large quarries, burning it at high temperatures, and creates all this carbon dioxide problem. So some species of single cell microalgae can biologically grow limestone through photosynthesis, much like growing a coral reefs. So this would create a net carbon neutral way to make Portland cement. There's research being done up the road for me here at the University of Colorado Boulder and the University of North Carolina Wilmington. So there's some interesting possibilities here. 1 to 2 million acres of open pond systems would be needed if we were to really say, like, you know what, we're replacing cement in the United States, traditional limestone for cement in the United States with microalgae generated limestone. We need about 1 to 2 million acres of open pond systems to grow enough to meet the demand for cement production in the U.S. But just as a piece of context, we use about 100 million acres of land to grow corn in the U.S. So it's a lot, but it's an interesting concept. We need about 1% of that, what we use to grow corn, to grow enough algae generated cement to create this carbon neutral solution. Cellulose nanomaterials is another one to discuss. This is a new class of cellulose particles with properties and functionalities distinct from molecular cellulose and wood pulp. As a result, they're being developed for applications that were once thought impossible for cellulastic materials. That's from the U.S. Forest Service. These nanoparticles are small, significantly smaller than cement materials. So when they mix with cement particles, they're small enough to absorb the surface of the cement particles and actually strengthen the final product. So we can see material strength actually increase by 20% and greenhouse gases cut by 1/3 by using these cellulose nanomaterials, again, like wood waste kind of thing. Cellulose fibers in concrete increase freeze-thaw durability as well. It creates more flexibility and provide a good finished surface, used to improve impact resistance and surface durability also. So some of these, as well as decreasing CO2 impact, also have some positive performance impacts too. And as well as like talking about all of these potential replacements or supplements to cement, another area we're looking at too is to recycle aggregate as well. So currently, unneeded concrete can be recycled, and usually it's crushed up and used for like road fill or something like that. We're seeing on some level concrete being crushed up and used again as aggregate. And I know there's some studies that have been going on. I believe that some have gotten as high as about 40% of aggregate in a new mix coming from recycled concrete. So there's certainly a chance there to save on materials, transportation, all that, and also, again, be able to reuse concrete that comes down, create more of a cradle to cradle type of concept where old concrete becomes new concrete. So we've talked now about some things to actually do in the material makeup of the concrete, but something else that we're seeing happen in the industry to a degree is this concept of carbon capture. So, taking the idea is that we take some of the carbon out of the process or out of industrial processes and put it back in the concrete in some way. So there are different technologies out there. I mean, the one that you might have heard of is called Carbon Cure. They actually take industrial waste CO2 and inject it into the concrete. Essentially it saves you a few percent. There are claims that can improve the strength of the concrete. I know that can vary. We're just starting to see it used a little bit in the precast industry. But there's also some studies going on for different things in this area. Team at Purdue proposes adding small amounts of nanoscale titanium dioxide to the cement paste, finding that it helps to increase the concrete's natural ability to sequester carbon dioxide. Again, once it's taken into concrete, it's entombed there. It's not going anyplace. Researchers at University of Michigan are also working on a composite engineered to react with CO2 and form minerals so the greenhouse gas can be stored in the concrete rather than become a byproduct. So some studies are happening on that front too. And then, as I mentioned earlier in the presentation, there's this concept of the carbonation sink. Basically, studies, in fact, this was in the IPCC climate report from 2021, I believe, estimating about half of the carbon emissions from cement productions are reabsorbed by the material when used in buildings and infrastructure. Cement carbonation sink absorbs an estimated 20 million tons of carbon each year, according to that report. Direct CO2 emissions from carbonates in cement production are around 4% of total fossil fuel emissions. I've seen a study that estimates that about 30% of all the CO2 from the concrete produced since like the 1930s has been reabsorbed into concrete over that time. So it's the idea that as concrete ages, it basically creates chemical reactions that suck in the CO2. So it's a long-term thing. And, again, we don't know the exact extent of it. Studies are still being done, but it's a consideration. It's something to also think about when we're thinking of a cradle to grave or cradle to cradle kind of concept. There are indications that concrete offsets some of its upfront impact over time. And we also have the idea of, as I mentioned in sort of our approaches, is doing more with less. And that's in the precast industry. We're seeing some really interesting things happen with ultra high performance concrete, which is a cementitious concrete material that has a minimum specified compressive strength of 17,000 pounds per square inch, with specified durability, tensile, ductility, and toughness requirements. UHPC building and bridge members will use materials more efficiently while also being able to span farther. Lower consumption of construction materials will be good for the environment because of potential to reduce carbon dioxide emissions. So the whole thing with ultra high performance concrete, or UHPC, is that it's so strong and light that we can do the work of what you'd normally need a lot more materials for. We're seeing this already coming up in some transportation projects, and some other building projects as well. So just as a comparison, traditional precast comes in at about 5,000 psi minimum strength and 700 psi flexural strength, used for wall panels, column covers, all the types of things that we talk about. Thicknesses ranging from 5 inches to 12 inches. UHPC is at 14,000 to 17,000 psi minimum compressive strength. Flexural strength is approximately 1,400 and greater. Products include rain screens, grand entrance cladding, urban furniture, interior solutions. Thicknesses range from a half inch to 3 inches maximum. So it's just a thin, super strong material. UHPC contributes to more sustainable construction by doing more with less. A couple examples here. It's strong and durable, greatly reduced water cement ratios, 5 times compressive strength, longer life cycle, reduction of materials and weight up to 70%, reduces the overall carbon emissions from manufacturing. Couple of these pictures here are a couple of case studies. One, Dumbo Townhouses is a 5-story in historic Brooklyn neighborhood using unique UHPC louvered panels, 18 feet long by 11 feet wide. This was done in 2015. The other one is the Gateway DC, lightweight ductile canopy and rooftop terrace for an open air pavilion. The iconic pavilion's roof level is accessible to visitors. The roof panels are just 1 3/4 inches thick. Each panel averages 171 square feet, ranging from 7 and 14 feet in length, with a gradual dimensional change in width from 9 feet to 2 feet over the entire structure. So super strong, flexible, a lot of cool things you can do with UHPC. So that's some things about the material itself and some of the things that we are either doing or working to do or investigating as an industry as ways to reduce the carbon impact. But also, individual producers are doing a lot to improve their own footprint as an industry. So one thing we're doing PCI as an industry across the country is starting to track LCA data more closely. We've really started a major industry initiative, and several producers have been ahead of the game on this. I certainly know Knife River here and some of the other folks in this region have done LCA work already and developed EPDs. So we're really trying to get that so that we have a good national baseline of where we're at. We want to emphasize product transparency, improve processes also for efficiency and sustainability. Just to again talk a little bit about the differences, and I'm sure you guys are aware of this stuff, but the types of life cycle assessment. Cradle to gate is just the impacts right up to the shipping of the product out of the factory. Cradle to grave covers that whole life, including maintenance, installation, deconstruction, all that stuff. And cradle to cradle is the concept that a material becomes, at the end of its life, is recycled into that material again. So when we're talking about within LCAs and EPDs, we're talking about different phases of the process. So the production phase is what basically covers cradle to gate. Construction stage is where you get the transportation to the site and installation. Use stage, which really is about 90% of the impact of a building, is its operational energy use over time, and any maintenance, repair, anything like that. And then end of life stage is deconstruction, demolition, transport to waste disposal, and everything that goes into that. So LEED version 4 and also just lots of different projects right now are encouraging this product transparency that requires EPDs, or environmental product declarations. And how we get to environmental product declarations is by first establishing product category rules, or PCRs, which are usually industry-wide kind of documents that specify what an insulated wall panel is, or whatever it might be. And then either industry-wide or individual companies or producers, in our case, will do product lifecycle assessments, and really dig into all that data, gathering every impact and everything that goes into it, so that they can then come up with this large stream of data, which is the LCA. And from that, it gets boiled into an environmental product declaration, third-party verified. You get kind of a snapshot of the impacts and ingredients that are in a product. It's sort of like the nutrition label on the box of cereal. So you kind of get a basic idea of what's in it. It gives you that transparency. So again, the process is product category rule, life cycle assessment, EPD, third-party verification, and submittal. So EPDs are being developed both industry-wide and company or product-specific in the precast industry. I think, we're seeing a good example here in Colorado. Actually, our Department of Transportation, the state legislature passed a like Buy Clean Colorado Act. I think it was a year or two ago, where they're going to be requiring EPDs on everything, both architectural, commercial projects, and also transportation. And CDOT, our Department of Transportation, actually got out ahead of this and reached out to the different industry players like us. And we've been working together to come up with the proper baselines and information gathering and working together. And I think that's an effective approach, so that we all can work together to create a better impact and do it in such a way that is, workable for everybody. So we're all working towards more sustainable, resilient structures. And as well as that, plant performance, and one of the advantages of precast in general is it is a very controlled and efficient use of concrete. It's done in plant conditions, monitored very closely. PCI certification is very stringent, so it's pretty tight in that respect. So many individual companies, even going beyond that throughout different sectors of the industry, are going above and beyond and doing even more. Goals and techniques vary, but here's just a couple examples of what some producers around the country are doing. So they're headquartered in Minnesota, and they've got plants in Colorado, Illinois, and Wisconsin. They're actively working on energy conservation, carbon reduction, sustainable building design, and waste management methods across their facilities. A lot of their facilities use fly ash, which reduces that embodied carbon in the concrete mix, like we talked about. Developing and sharing EPDs. They've been moving on that for a while. They've retired 3 outdated production facilities, replacing them with new sustainable precast manufacturing facilities that are more energy efficient and reduce waste. They work with carbon capture firms to mineralize and insert reclaimed gas into the concrete mix. They use a new cladding system that uses 65% less concrete, doing more with less, as we talked about. Lighter weight panels also help reduce the size of the structure needed to support the exterior enclosure, so you're just reducing carbon and material all around. Knife River, headquartered in North Dakota with locations in 14 states, working right now on a state-of-the-art precast manufacturing facility in Washington. I don't know if anybody from Knife River is here, but maybe at the end you can talk a little bit more about that if you are. New facilities seeking Concrete Sustainability Council certification, 0 untreated water emissions from processed water, wasted concrete will be recycled on site. Ultra-modern concrete batch plant with better controls allows for optimized mix design to reduce carbon footprint by as much as 20% on certain mixes. Utilization of electric concrete delivery system eliminates the use of diesel engine-driven delivery equipment. They have a roof design to support future utilization of solar power. Site is also laid out to minimize wasted transportation and accommodate long-term growth of the business. So just being efficient about how you do things can really save a remarkable amount of energy too. Looks like we already had that one. So doubled up on Knife River there. So Metromont is another company. Minimize building material waste with efficient production processes with 2% waste is created, and up to 95% of that waste is reclaimed or recycled into other products. They recycle all their concrete slurry water, and reclaimed aggregates is becoming more common in their manufacturing facilities. Metromont is one of the largest recycling and reclaiming processes at its Greenville, Hiram, Richmond, and Florida facilities. At one plant alone, they recycle about 6.3 million gallons of water per year. Typically 80-90% of the materials are extracted, manufactured, and delivered within 100 to 500 miles. So they use a lot of efficient techniques and products there as well. There are lots of industry resources to go to. So PCI, PCI.org, there's lots of information, both about our certification program and also about sustainability efforts within the industry. Some really good information there. In fact, there's a new designer's notebook that just came out that's talking about EPDs and how to think about those. That's a really good resource. If you guys are interested, feel free to reach out and I can send it to you. But also NRMCA is doing some great work. The National Ready Mix Concrete Association, buildwithstrength.com is a really, really excellent industry resource for sustainability information. And then a relatively new player on the scene that's got some great research coming up too is the NEU, which is an ACI Center of Excellence. So ACI is the American Concrete Institute, and they've got some really good information there as well. So in summary, concrete is a durable, efficient material that inherently provides the versatility and resiliency needed to meet the multi-hazard requirements and long-term demands of high-performance structures. Beyond excellent lifetime performance, the concrete industry and the precast industry is innovating and working tirelessly to reduce its carbon impact in the short term. Promising new technologies and techniques enable us to build for tomorrow. And that is what I have.
Hi, Jim. Thank you so much.
Yes.
This is Ellen.
Hi.
And I'm just jumping in. We have a question from John. But first of all, I wanted to just thank you so much for that presentation. That was very, very interesting and super relevant, I think, for this audience to hear about.
I appreciate that. Thank you.
You bet. You bet. So John has a question. Are there regional PC producers who are experienced in implementing the greenhouse gas reduction strategies that you've shown?
Yes, I think, is anybody from Knife River on the call today? I thought I saw somebody on earlier, maybe not, but yes, I know that they certainly have been doing a lot. In fact, they were a big resource for me putting this together. They've had some touch on just about everything we've talked about, or at least explored in some way, and they're doing some really innovative process things too. So they're in your neck of the woods. And also I know that in my group, like Missoula Concrete has done some really cool, like they actually have the first LEED platinum building in Montana. That's a bank that used, credit union, I think, that used concrete that was free of Portland cement at all. It was all different, replacement materials and things. So there are certainly some PCI producers out there that are doing that kind of work.
Excellent. Thank you. John, did you have a follow-up? You're free to unmute yourself.
That makes me wonder if are you getting support from the engineering community in terms of specifying the products?
That's an excellent question. Yes and no. I mean, I would say, it's a discussion we're having quite a bit as an industry right now. A lot of these things. Now, again, a lot of what I talked about today is relatively new or kind of coming online. Just as an example, like, the carbon capture thing, so Carbon Cure is one firm that does that. And they've been doing a lot of work with producers around the country. So this idea of kind of carbon offsets is a thing. We're doing, quite a few producers are getting more comfortable with their engineers with using these different replacement cements and even the PLCs and the LC3s and things like that. Absolutely. Like there is, I think there has been some hesitation I've heard, with some of the, just because it's new, PLC and LC3, because those are starting to be required by a lot of departments of transportation and things like that. But to my knowledge, I haven't really heard of any issues with folks doing it. I think sometimes they have to make some slight adjustments, but as with anything, engineers will hesitate a little bit, but it's also important because we don't want to just jump off the pier and say I'll just use this and everything will be fine. We want to make sure it has performance that it needs to. But I'm finding good within the precast industry. I'm finding really good collaboration on that. In fact, we're just launching a new sustainability committee that's going to be made up of folks from the engineering and architecture sides of things and hashing a lot of the stuff out in terms of our processes.
Thanks.
Thank you.
Excellent.
Good questions.
Thank you so much, Jim. Well, it looks like we are right up at time. Does anyone have just a short question, or should we just go ahead and let everyone go off to happy hour or
Oh, yeah.
driving
That's
home
good.
or whatever?
Yeah. There's a good question. What are you
Wherever.
having for happy hour? Yeah.
Yeah.
Well, I want to thank
right.
everybody for taking the time. Seriously, appreciate it.
Yeah, thank you so much, Jim. Really, really appreciate your time to educate us today, and hopefully it gave everyone a little food for thought.
Indeed. All right. Feel free to reach out, by the way. It's jschneider@pcims.org if you have any questions.
All right. Thank you so much. And thanks everyone who joined. Have a great
Thanks,
night.
everyone.
Thank you.
Bye, Jim. Thank you.
Thank you.